Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Warp25, published in 1987 by Datel, part of the Action Replay support utilities. A deep technical dive on how this one works was requested along with the Epix fast load, and I've already done the Epix fast load, so I'm going to have a look at this one today. Let's load this up in ICU64 along with Vice so we can see what it looks like. I will add all of the download links to the video description below, so you can also download a copy of this if you don't have it already. I will also include links to my updated tools and documentation source code repositories, so you can also see all of the documentation that goes along with this video. So this is what you are greeted with when you start running the utility. I need to make a very simple D64 image containing the file that I want to transfer to a new disk image. So I'm just going to create a nice short name, t.d64, there we go. And I need a suitable file to put inside here, so I want something which is a bit large, but not too large. I'm going to use my test multiplexer demo. Just going to rename it to a shorter file name, so I don't have to keep on typing in the great big long file name all the time. Let's call it TM for short. No, TM, there we go, not the shifted character set. Let's make sure that's saved. There we go. It's just a quick test of my multiplexer code. So it shows a sprite grid, or a sprite formation rather, and then whizzes some sprites around. So when the disk turbo loader loads this file, this is what we should see. It should work. Let's mount the disk image that we just created into drive 8. There we go. I also need drive 9 enabled, so let's make it a 1541-2. Now for drive 9, I need to attach it as a G64, not a D64. A D64 does not contain enough information to accurately reflect all of the data on a disk. That's why the G64 disk format was created. D64 contains raw bytes, which are basically sent to the Commodore 64 without any encoding. I mean, the emulator encodes them internally, but a real disk image uses what's called GCR encoded data, and we'll get into more detail about GCR encoding later on. But suffice it to say, we need a G64 file to reflect all of the data that the Warp25 Super Bootmaker is going to put on the disk. I almost forgot, I need to press F3 to change the output device to be device 9, which is where the G64 image is located. So looking at the disk directory on device 8, we've got the TM file there. So just type in TM. I used option 3 for transfer a file. So we can see actually that it's loading the file from the D64 quite quickly, and it's loading that into memory. So and we've got this nice multicolor border effect, and each change in the border color is a byte, I think. Yeah, a byte read from the disk. If we step into the C64 code in the monitor debugger, then we can see, look, it's doing a load A with D012 and doing some mathematics and some comparisons. This looks like it's doing a bad line check. It's avoiding the bad lines which are introduced where the VIC chip steals some cycles from the CPU. It's doing this because then it doesn't optimize what looks like a 2-bit copy. It's extracting 2 bits at a time for 4 cycles or 4 iterations. It's an unrolled loop, or it's unrolled code basically, but it's creating a byte 2 bits at a time from the drive. So it's using Initially, it's using a relatively fast, actually quite fast, 2-bit transfer protocol to read the file into memory. And then, of course, it will write that file from memory back out to drive 9. But we're not there yet. But a 2-bit transfer protocol with a standard format disk is not new or surprising. If you watch my videos, then we've gone through several different disk turbo loaders. The screen has turned off, and we seem to be writing data to the disk with the screen turned off, which is rather interesting. And we seem to be running some code up in the kernel space as well. So we can see, using the graphics map or using the text screens mode, that we can see the test multiplexer demo code has already been loaded into memory. The screen is there, and that's because the program file that's being transferred to the other disk doesn't load over the screen memory. I think this is geared more towards transferring large basic type files, but there seems to be a lot of data there at the end of memory, doesn't there? Hidden underneath the kernel ROM routines. So we've got what looks like at least a couple of encoding tables, perhaps. And we have also got a whole bunch of code there to deal with the superboot disk turbo menu and everything else like that. So let's start using the machine code monitor windows to look at what the drive is doing, drive 9. We're not really interested in drive 8 because that's just reading data from the disk. We're more interested in what it's doing when it's writing data. We'll also bring up some documentation for the 1541 ROM routines. Okay, this is getting the number of file names and stuff like that in the drive ROM routine. Okay, fine. Okay, it's not running E7C9 in the drive ROM. That's a quirk of the monitor debug windows. It actually hasn't updated yet. There we go. That's the real address. EC79 was the address in the C64's kernel. We're actually running drive code now. We can tell that we're running drive code because we're running code from one of the buffers in the drive's RAM. The drive only has a limited amount of RAM, so all of the RAM is grouped at the beginning of memory. From C000 all the way up to FFFF, you've effectively got the drive ROMs. So we're not in the drive ROM code, we're definitely in the drive RAM, and we're definitely running drive code. We see this pattern often, BVC, and then the same address where the BVC instruction is. And that's something quite special to the Commodore 64 drives, is that it uses the overflow flag, which can come in as an external pin on the 6502, and it uses this pattern of using the BVC instruction to test the overflow flag, and the overflow flag comes in on the pin on the 6502, and that relies on some external circuitry, and that's when the drive head has finished processing either read or write data. So there's a little timing signal or a signal from the drive circuitry which indicates when the drive head has done stuff. So that's the quickest way of synchronizing the CPU with the overflow flag with what the hardware is doing. So already we seem to be having some quite optimal drive code to do what we're not quite sure yet, but we know that it's roughly doing some drive writing or data writing with the drive while the screen is turned off on the Commodore 64. I'm guessing it's really important to have the Commodore 64 screen turned off for this because there's probably some very tight timing in terms of data transfers. So we're just at the beginning of this journey of decoding what all of this code does. It's going to get quite involved, I have a feeling. So this is one of the drive's control registers for the disk head and read-writing mechanism and stuff like that. VIA2 is at 1C00 onwards. VIA1 is at 1800 onwards and seems to deal mostly with, in what we're interested in, serial communication with the Commodore 64. VIA2 seems to mostly deal with drive related mechanics. So we're storing some details into 1C0C there just to verify what it's doing. So the last 3 upper bits of this byte are 110, most significant bit to least significant bit. So 110 up at the top is low output. Okay, so it seems to be outputting data. The data direction register is also set to output. It's all set to be 1 bits because X is FF and X is going to go into 1C03. Okay, X seems to be used as like a little counter. That's the 0 page for the 1541. This is the ROM for the 1541. You can see here in the ROM for the 1541 that BVC instruction, branch on overflow clear, is used very often because that's the code pattern that they use for synchronizing the 6502 with the drive's hardware. The code on the C64 side that's running is also doing some serial port synchronization there as well. But basically, this Wikipedia describes it in more detail. But basically, this describes how the BVC instruction can be used to synchronize with the drive hardware. That's the important part of that paragraph highlighted. Anyway, this seems to be doing some quite optimized drive code to write data pretty much as quickly as it can. It's storing patterns of bytes, and then it looks like it's storing bytes that come from 700 indexed with Y and also 600 indexed with Y. So it's probably saving out or writing out a sync marker to the disk and then writing out pre-calculated data to the disk track. It looks like it's saving out to A2 bytes and then saving out the full 256 bytes or 100 in hex. Or it might be doing 2 lots actually. It looks like it was doing 2 lots of 0 to A2, was it? But yeah, this looks like writing code in the drive side, just adding some debug notes so I don't forget what's being worked out. As I say, I think this is going to get quite complicated. I'm using the notation of using 9 colon to indicate device 9 or C colon to indicate Commodore 64. And we're not going to really be doing 8 colon because we're not interested in the drive reading functionality. We're only really interested in the drive writing functionality at this point. So yes, this is loads Y with A2, then loads from 700 and then 600 and then stores into the drive output bytes at 1C01, and it does that twice. So it does it from 700 and 600, Y for A2 bytes long. Okay, and then it RTSs. That's fine. Once it RTSs from the drive code, RTS is returned from subroutine, jumps to 345. 345. Great, the disassembly windows got confused. That's intriguing. I can see a CLI coming up, which is a clear interrupt flag status in the status register, which enables the interrupts. That's coming up soon. It's doing a JSR to 300. This lets the drive job code processing actually poll. The drive code, the drive ROM, has this really weird, convoluted perhaps even, mechanism of polling for command codes and doing that during an interrupt. It allows the drive to open files and search for blocks and read blocks and tracks and sectors and stuff like that. But anyway, 1800 is VIA1 on the drive code side of things. That's the serial port communication with the Commodore 64. The Commodore 64 seems, okay, the Commodore 64 seems to be sending data 1 bit at a time to the drive. 1 bit grouped in 8-bit chunks, so that's 1 byte at a time using 1-bit transfer protocol by the looks of it. So once the Commodore 64 has read at nice fast speed, relatively fast speed, using that 2-bit read protocol, 2-bit transfer reading protocol rather, it then proceeds to send that file data back to the drive code for optimized writing, but with the screen turned off, and using a 1-bit sending protocol from the C64. That's, fine. The overhead here is not going to be, while writing the data, you're not really interested in making it super duper fast by using a 2-bit transfer protocol from the C64 to the drive, right? You're more interested in making the code easier and reliably sending that data, so you might as well just send it 1 bit at a time, 8-bit groups for 1 byte at a time, using a 1-bit transfer protocol. That's perfectly fine. So 300 in hex on the drive side of things seems to be a receive byte method, or function if you like, which receives a byte from the C64. In this case, it's receiving a byte and then storing it in E and F, and then RTSing. This is where we're still in the code where the C64 is sending data to the drive, and then the drive is going to come along and then write that data using a very low level drive writing functionality. So we can pop out of this now. Now, the drive seems to be reading a couple of different its internal kind of like command codes, if you like, almost like it's looking for F2, it's looking for F1, looking for F0, looking for F5. So at this point, maybe it looks like the C64 is sending command bytes along with following data and sending that to the drive code to control how the drive for the C64 to control how the drive writes the data to the disk. So at the moment, it seems to be parsing command F2 quite a lot. Maybe command F2 is write data. There we go. So yes, JSR to 3C8. So let's note these findings down. We might come back to the command bytes later on, although I'm really more interested in the how Warp25 loads data so quickly from the disk rather than how it is precisely writing the data to the disk. Although to understand how the data is written at a certain level can be useful for then decoding how the data is read later on. Just finishing writing those notes. Yeah, there's the code that we're looking at now in the disassembly window. There was a weird byte just before the opcode, so that was interfering with reliably disassembling this code. So here we are. Let's step into the F2 command processing, because this seems to be write block. It seems to be getting some. It seems to be comparing the value in E with the value that's in 2.2 in the 0 page in the drive's memory. E and F seems to be, perhaps that's track and sector. It was already part way through writing data to the disk, right? So maybe that's track and then sector. And then maybe what is in, let's have a look, what's in 22 location, 0 page location 22. It helps if I don't make typos. There we go. Okay, so location 22 also seems to be 2, which seems to match. So maybe this is track 2. If it is already on track 2, then it doesn't need to move the head around to get to a different track. Looks like this is doing some reads from the serial port. So it's receiving data again, by the looks of it, from the Commodore 64, flagging to the Commodore 64 what it's doing, perhaps. Maybe the Commodore 64 is storing this data that it's sending back, but I don't think so. I think it's just receiving data from the Commodore 64 and then storing it in the drive's memory as 700. That's intriguing. What is the Commodore 64 doing? The Commodore 64 is reading from E100, E200, E000, X. Oh, look, so, okay, so the Commodore 64 seems to be reading very quickly from a pre-computed table and then storing into DD00. So it seems to be doing some kind of like computation into those tables. Maybe they're temporary tables, maybe they're bit tables for optimized serial port access for the drive. Maybe they are encoded tables for data encoding for the bytes being sent to the drive and then being written to the drive. Maybe it's done some encoding, pre-encoding on the Commodore 64 side. Anyway, this data, these bits, whatever they are, yeah, coming from those tables there, that's being sent to the drive. The drive's receiving it, and then the drive is receiving that into a buffer and then writing it out. Now it seems to be doing some writing out of the bootloader stuff. So with Warp25, the bootloader has to be readable by the drive's ROM routines. So the bootloaders have to be in standard 1541 GCR encoded data format. But the rest of the data, which is turbo loaded, is not. That's how it gets its speed pretty much. We can use the compare tool to see if there's any difference between the formatted disk image, G64 disk image, and then the updated G64 disk image. So we'll have a look at the hex binary difference compare with this tool to see if there's any differences. Original file on the left, updated file on the right. Oh, it can't update, it can't read the file because it's held open by the emulator. Let's just close it, and then the binary difference tool should be able to read it. Right, there we go. So, oh gosh, wow, okay, so original disk image on the left, updated disk image on the right. We can see that there's some quite significant differences in terms of large blocks of data in the disk image that have changed. There are sporadically changed bytes as well. Okay, all of those have changed. Okay. And then there's significantly changed data at the beginning of the disk image as well. And then there is some disk image data that has been changed towards the end, and then the middle. I'm guessing the middle one is the tracks and sectors and blocks used for the disk directory and everything else. But we also seem to have a large amount of data that's been changed at the beginning of the disk. And that's the data that we saw, I think, being written for the test multiplexer program file. Okay, so there's quite a large number of changes to the disk image. Let's close that. Let's see what the disk image does when we load it now in the emulator, so we can see how quickly it loads this Warp25 format disk image now. And then we can begin to understand the Warp25 disk turbo loader. Looking at the disk directory listing, we can see that there are 3 files. Warp25, copyright 1987, National Replay version 3, and then the $TM file, which is the test multiplexer file. So if we have a look at that disk directory now in the C64, we get the same kind of thing. Load, comma 8. And if we do just load, comma 8, and then list it, we get, rubbish. Okay. That means that it's no longer obviously a basic program. It is a program which has significant data elsewhere. So we load it with comma 8, comma 1. And then let's see what happens. And it loaded some auto run code, and that, wow, okay, wow, that's really fast loading, isn't it? That wasn't even warp speed in the emulator. That was just loading it. So yeah, that was really very, very fast. And the code initially started with some auto run code. So we're going to put a ranged breakpoint from 100 to 400 to see if we can trap out the initial auto run, auto boot code, if you like. And we can see straight away that it's getting into code at 34A on the Commodore 64 side of memory. This comes from an indirected jump through 0326. Well, there we go. 0326 is... Yes. Anyone guess? Anyone guess before I open the 0 page listing? It's going to be the chart out routine, right? Yeah, there we go. Chart out routine. The usual kind of way, there are many different ways of doing it, but it's one of the usual kind of ways of hooking your auto run code, or auto boot code if you like, to cause your code to get executed as quickly as possible. So let's open a disassembly window now for the drive side of things. The memory address is not correct until I step, of course. Must remember that. That's a really weird bug. There we go. So the drive seems to be merely running some code in its default ROM at the moment. We can see that because it's up at E85C on the drive side of things. The C64 is running its auto start code now. So what is the C64 doing? Well, the initial code seems to be restoring the vector at 326 and 327. BB and BC, if I remember rightly from my C64 knowledge database in my brain, basically, BB and BC seem to be the file name pointer in 0 page. So it seems to be doing something with the last known pointer to a file name. Huh, okay, so it's replacing the second character with the PETS key value 3F. Just double checking. Yep, BB and BC, current file name address. There we go, file name pointer. So yeah, it's changing the second character because Y is 1 rather than 0, so it's changing the second character. And there we go. There's the file name that we passed in. That comes from the basic load command, right? And it's changing. It's going to change question mark star. So it's going to change the star to something else. 3F is question mark. Of course it is. Yes, it's there. We go. Well, location 9FFC is 3F, and that shows question mark. So yes, it's changing the second character of the file name to be question mark. But it's also copying the file name to 200 in hex, Y there at 35D. And then it does some comparisons. Okay. All right, so what is it doing now? Okay, then it turns off the screen because D011 is a VIC screen control register. Okay, so we'll have that breakpoint there at 370 because we know 370 is going to be turning off the screen, or rather 36B rather, and then just after 36B turning off the screen, it's going to start doing other stuff. So we'll execute ahead to that breakpoint. There we go. Now it's doing FFBD set file name parameters, right? These memory address locations, especially in the C64's kernel ROM, you kind of like remember them after a while of dealing with them for so long. But yeah, FFBD set file name parameters, pretty sure. Let's just check. There we go, FFBD set file name parameters. Cool, okay. And that just stores AX and Y into the 0 page memory locations. Then what is it doing? Seems to be, after that, seems to want to be, okay. Seems to be looking for A star. Okay. Or telling it to start looking for A star, and then it seems to be doing something with a memory execute command and copying that to somewhere temporary. Okay. So that's intriguing. Okay, so it's setting up the file name of A star. No, it's not. And then it's doing 3AF. 3AF, 3B0, run colon. Of course, it's storing run colon into the keyboard buffer. Okay. Yeah, of course, 276 is the keyboard buffer. But after that, after the run colon, look, there is a m-e command. Great. Just double check 276 in 0 page locations, extended 0 page, 276, blah, 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 blah. Keyboard buffer Q, FIFO. Oh, there we go. So yes, it's putting run colon into the keyboard buffer. Then it's going to F4A5, and F4A5 continues the standard load RAM entry at 389. There, it's doing a JSR to F4FA5. Okay. Okay, that's fine. So it's storing the accumulator into 9D just before JSRing to F4A5. So we'll put a breakpoint after that, and we'll see once we continue executing. It seems to load a chunk of data all the way at the end of memory. Okay. So it's continuing to load data, a chunk of data, all the way at the end of memory, pretty much. That's what it looked like. It's transferring A to X and then branching on carry set 343. Okay. That's probably an error check, to be honest. It probably goes back and reinitializes everything and tries the load again. We'll step through this code to see where it gets to next. I don't think it's reached an error condition. No, it hasn't. It then stores F into, which is decimal 15, to B8 and B9. B8 and B9 are, oh yeah, logical file number and secondary address. So that might be, well, it's setting up the command channel, right? So it's doing like the equivalent of opening command channel to the drive, okay, and then I bet you it's going to send the m-e command now. It's loading the value 3b5 in hex in X and Y now, and doing another ffbd, which is setting the file name parameters. Do you remember what 3b5 is in memory? I do. It's the m-e command. It's actually the m-e command with a low byte, high byte, and then what looks like at least 17 bytes in hex total. So it's actually sending not just the start address, it's sending the start address plus A912850E A9. Okay, so it's sending machine code along with the m-e command. That's quite a cool way of optimizing your communication to the drive using the kernel routines, is to bundle extra code with the m-e command. And you can do that because the commands at the drive level, when you're sending commands, you can actually send a bit of data along with them. It is using the file name parameters, and then it's using FFC0. So file name parameters is a FFBD, is that routine there. And then the open routine is going to be a FFC0, right? Let's make sure that I've got the right breakpoint in the drive side of things. Yeah, let's delete all the breakpoints. Let's not have a typo. There we go. Right, getting a bit confused there. Semicolon and colon look really similar, especially when they're so small on the screen. FFC0, yep. FFBD set file name parameters, of course, we know that. And FFC0 was open a file, right? And it does open a file with the secondary addresses and everything set to 15 and 15, right? So this effectively uses the kernel routines for sending m-e over the command channel to the current drive that's being used for this load. After it does the open, which is the m-e command, or sending the m-e command with the extra bundled machine code and the start address, it's doing a set interrupt flag, SEI there. Just double checking what this code does. Yeah, I think that's pretty much the code flow so far. on the C64 side. So we'll put a breakpoint on that SEI instruction there, the set interrupt flag. And that disables interrupts pretty much on the C64. It disables IRQs. It doesn't disable NMIs, of course. And then after the C64 gets to that code, then it's, oh gosh, look, it's twiddling location 01. And you'll notice if I disassemble what's at FE00 there before, and now if I step the instruction over and then show you the memory afterwards, you can see the memory looks a lot different. And that's because storing $35 into $01 causes the kernel ROM in the C64 to get switched out and the RAM underneath the kernel ROM to be visible. So it's jumping to this code that at FE00 that was loaded right at the last minute, which was loaded during that continue standard load RAM for a bit code at 389 there in the Commodore 64 side. So let's step into that code at FE00 now, and FE00 then jumps to FEB8, and this does some stuff. So, okay, so the memory at 200 in hex is of course the updated file name now with a double question mark and a TM. And FE71, looking at this pattern here, FE71 is logically going to be sending this file name to the drive code. The drive code that has been started to be executed by the m-e command. Great. So now we have the drive starting to run its drive code, pretty much. And we also have the C64 running its code. So we're debugging code now. In parallel, we've got kind of like, if you like, we have two threads or two processes running. Processes would probably be a more accurate description because they're running on two different processors now. They're running on two different CPUs. One in the drive and one in the Commodore 64. Because don't forget, the 1541 drive in C64 world has its own CPU. That's how we can debug the drive code, because it's running on the CPU in the drive. So we seem to be what looks like sending data 1 bit at a time to the drive. How do we know it's 1 bit at a time? Well, there was a load X with 08, and then it's doing this loop 8 times, so it seems to be doing a 1 bit, a relatively slow but reliable 1 bit transfer protocol. Meanwhile, the code on the drive code side of things starts executing at 205. And wow, okay, so the drive code seems to be doing stuff already with location E and F and also F9 in the drive's 0 page. Okay, so let's... So just adding some more debug notes. Let's just double check the 0 page locations in the drive. E and F, track and a sector for buffer number 4. Okay, and that's setting up track and sector in hex 1211, which is 18, and track 18 in decimal and sector 17 in decimal. Okay, F9 is the current command being executed by the drive, or the current buffer in use. Okay, so the drive code immediately seems to want to start reading that particular block at that track and sector. And the drive code immediately seems to want to ask the drive's ROM routine directly to start processing that drive command by JSRing to D586. Right, so if we have a look at D586, in the drive ROM disassembly, D586 is in the middle of, oh, there we go, read block. Okay, So yeah, instead of asking the job code mechanism, it's just calling the job code mechanism processing routine directly to read that block from the disk directly. Fantastic. After reading that block, the drive code then runs more code at 700 in hex. And that's because the memory used for buffer 4, if I remember rightly, buffer 4 uses memory location 700 in hex. So that kind of makes sense. There we go, buffer 4 700. That's the drive 0 page or extended 0 page memory map. Or rather just the beginning of memory map. Okay, so 700 currently contains nothing really interesting. And now, after that, there we go, 700 now contains what looks like interesting machine code. 78 is set interrupt flag. Opcode, if I remember rightly. So yeah, that looks like it's or at least going to start executing some more drive code just after reading it from that track and sector, that block. Great. So that block is also going to be in standard GCL format because the drive ROM has to understand it. So then we have this kind of like startup code where the first byte at 300 in hex is actually changed to be an RTS instruction because RTS is 60 in hex. Why is it doing that? Don't know. We'll find out. Yeah, it stores an RTS instruction, then immediately JSRs to it, which then returns from subroutine. Back again. Is that so? Oh, that might be so this code can deduce which memory page it's running in, because then it might read that value from the stack. Oh, that's an interesting way of doing it. So when you do a JSR, it pushes 2 bytes onto the stack to indicate the return address. And so that load a 100, x where the current stack pointer is an x. Yeah. That's reading its own return address, it's reading its own high byte. Okay. So then this is checking to see where this buffer is located, and then it's basically ensuring that this buffer, wherever it is then relocated to a known memory address at 700. And if the buffer is the same, then it just copies into itself again with identical data. So that's perfectly fine. But if not, then it will it relocates the buffer to a known memory location and then jumps to it. Look at 724. It jumps from 721 to 724. Oh gosh, that's a really interesting way of doing it. But cool, I quite like that code. That's a really useful, good way of determining which memory address you're running from, right? Is to read it back from the stack after you return. Okay, I like that. Having a look at the code at 724 on the drive side of things, we're copying values from 753 and storing them at 0, x. And 0, x is all of the command buffer bytes and also track and sector information for those command buffer bytes. So the 1541 drive default ROM operation operates on a principle of having job codes and track and sector information that you associate with those job codes for reading and writing blocks and stuff like that, and it processes jobs. It does that. I don't know why. It's quite a complicated way of doing it, but I think it's, to be honest, it's a bit over-engineered. But hey-ho, that's what the process is used in the drive ROM side of things. So you can choose to work with it or not. But basically, at the moment, it seems to be sending job code data, copying job code data or job data from that memory location, and then storing it into the command job code mechanism there. And look, it's doing a CLI at 72F, which basically then says start processing these jobs, and then immediately it's checking the job return code status for all of those jobs, 0, 1, 2, and 3, those command code or job entries, if you like. It's looking for any negative values, and then it waits for all of those jobs, 0, 1, 2, and 3, to finish or to complete. So the command code for 80 is basically read. So it's basically saying read, and it's only doing that with the first 4 jobs. It's basically saying read track and sectors, so read specific blocks, one after each other, and then wait for all of those reads to complete. In other words, wait for all of them to not be minus. And then after that, you know that all of your buffers in the job command code buffer structure, you then know that those track and sectors, those blocks from the disk, are successfully read into the relevant buffers associated with each command or job code. Those last 2 bytes aren't used. It's only the first 4 pairs because it's setting up command code or job number 0, 1, 2, and 3. So there we go. So those are the pairs of track and sectors. 12 and 9, 12 and C, 12 and F, and 12 and 12. These values are in hex, so you can convert them to decimal if you like. That's going to be track 18 sector 9, track 18 sector 12, track 18 sector 15, and track 18 sector, what was it, 18. Yep, because 1, 2 is 18, and C is 12, and F is 15 in decimals. So yeah, it's basically, oh gosh, wow, okay, so it's reading 4 blocks, and then comparing the overall status with 1 as well. That indicates a successful read, if I remember rightly. If it doesn't work, it seems to retry the whole process as well. Branch are not equal to 726. 726, if I remember rightly, restarts the job code processing. Job code copy, and then it restarts the job code processing. Look, okay, great. So the set interrupt flag disables the interrupts which stops job code processing, and then it copies job code information in and then clears the interrupts which starts the job code processing, and it reads all of those tracks and sectors blocks, basically waits for it to complete. So we have a whole bunch of data and code now in those command code job code buffers. It then jumps into code at 345, which is more of the turbo loading code now. Pretty sure that's going to be the case. Okay, first thing it does is JSRs to 300 and then stores the result into 197, compares Y with 16 or 10 in hex, and then branches around again. So yeah, look, this is reading this is reading bytes from the C64 sent to the drive and then storing them into that memory location there. And that's, I'm pretty sure, can you guess what the C64 would be sending to the drive? It's the file name. So the drive stores the file name at 197 after loading all of this data and all of this extra code. So while the C64 is sending the file name 1 bit at a time to the drive, of course the drive is synchronized with what the C64 is doing, so because there's this 1-bit transfer protocol, it's very reliable, very synchronized. So we don't need to worry about the speed of the code per se between the drive and the C64 at this point. Oh gosh, okay, so the C64 then starts to receive data from the drive, and then it's starting to store that data at A3, Y. So 0, Y, but Y is A3, and it does that for A3 to AD. So it looks like it's receiving file information from the drive, probably start and end address and other such things. So after running to the next breakpoint, on the C64 side, A3 and A3 to AC rather, contains, there we go, 0108, which is low and high byte of the start address in memory of the loaded program file. A3, A4, yeah, that goes into AEAF. Okay, yeah, so it looks like program related data, start address, end address, maybe that kind of stuff. Okay, it's moving what looks like start address around into different 0-page memory locations. Looks like it's checking something for FF. That's probably a low successfully found indicator, right? Anyway, it's continuing to execute on to FE71, which gets another byte from the drive, stores it into AD. It's loading and comparing, but then throwing away the result. Okay. I don't know why it's doing that, actually. It's not really checking the result of the compare, but okay. Okay. So now the C64 is checking the serial port for a particular flag from the drive, which the drive hasn't flipped yet. So the C64 is doing that bit and BVC instruction pair, and it's continuing to execute that in a very small, tight loop. The drive code side of things, however, we've cleared the interrupt flag again. It seems to be storing track and sector information into E and F again, and then sending command code 80 to read another block of data. Great. Wow. How many more blocks of data is this drive code going to read? Gosh. So it's just one more extra job code this time rather than 4 in a row. But still, okay, it's reading yet more data. Fine. It's reading standard GCR encoded data as well. It's not reading any of the special encoded data yet on the disk. We know that because it's expecting the standard drive ROM routine with its job code processing mechanism to read this data. So it has to be standard drive GCR encoding. At this point, the Commodore 64 is waiting to receive information from the drive. When it gets to this point here at FE21, where the NOOPS NOP instructions start, that's where the drive really begins its code for receiving actual information. It seems to do it for a number of iterations that are in the Y index there, and Y was being loaded with the value $50. If we look at the code that was just after that, then it seems to load from DD00 and then do 2 shifts to the right, and then EOR with DD00, 2 shifts to the right, EOR, 2 shifts to the right, and then a final EOR, and then uses a PHA instruction, wow, to store the result of that onto the stack. Each of those 2 shifts followed by access to DD00, which is the serial port bits which come from the drive to the Commodore 64. Because it's doing 4 lots of those before storing the result onto the stack, it seems to be reading 2 bits at a time. When the Commodore 64 is receiving 2 bits at a time from the drive code on the right-hand side, however, seems to be loading values from 146, Y, and then using that value to then load more values from tables at 690. Okay. So values from memory are read from the drive code and then stored directly to its serial port, and then an opposite value, if you like, or an encoded value is read from a table and then also stored to the serial port. It's probably an opposite value. and then it's shifted. It might be an encoded value, and then it's shifted. Okay, so the drive is reading bytes from memory, and I have a feeling those read bytes from memory are coming from the disk. They're being sent very rapidly to the Commodore 64, and the Commodore 64 is precisely timing these accesses to the serial port registers along with those shifts and then the PHAs. It's doing 3 of those full byte, so I think it's pushing at least 3 full bytes onto the stack for every iteration through this loop with the Y counter set to $50. With the drive code on the right hand side, the important access to the memory, which I think is storing data from the disk, is with index comma Y there, and it loads X 146, Y store X at 1800, which stores it back into the serial port. And then it loads accumulator with 690, X, and then it stores that result into the serial port. So it seems to be using data read in probably from the disk and then using that data to store into the serial port and then actually to then access a table to load a new value to store into the serial port to send back to the Commodore 64. And then it shifts that value and then stores it into the serial port again to send to the Commodore 64. And then it repeats this with tables so at tables at 146 and then 700 and then 751 and then 7A2. These tables are roughly 50 in hex apart. Well, the tables at 700 and 751 and 7A2 are at any rate. The one in the stack at 146 is not, obviously that one's much further apart from 700, 751 and 7A2. But there are 4 tables there are 4 areas in memory which contain what looks like data read in from the disk. And then there are 4 table access blobs of code, if you like, which then store this into the serial port. So this looks like the data from the disk is partially encoded and then re-encoded with some lookup tables. And those lookup tables seem to aid in transferring the information to the bits expected for the serial port, which is a really fast way of doing it. But it's using quite a lot of memory, but it is a really fast way of sending this information in an optimized way over the serial port registers from the drive. The Commodore 64, on the other hand, can afford to shift out 2 bits at a time from its serial port register, so that's okay. So while there are 4 bytes of raw encoded data read in from the disk, it seems to result in these tables and the shifts involved. These tables seem to then result in 3 bytes being received on the Commodore 64 side of things. So there are these 4 chunks of memory block range accesses on the drive side of things, but there are only 3 bytes worth of result on the left hand side. So it seems that these tables have been optimized to decode the bit encoding method on the disk, as well as being optimized for the serial port register stores on the drive side of things as well. And that's because, if I recall, the bits for the serial port output for the clock and the data outputs are not adjacent on the drive's VIA registers, whereas on the Commodore 64 the input, clock and data are 2 adjacent bits on bit 6 and 7, the two most significant bits. So it's easier for the Commodore 64 to decode 2 input bits at a time, compared to it's more difficult for the drive to encode its 2 output bits at a time on its output lines from the serial port. But using large tables like that on the drive code side of things, it makes it a lot quicker. So the code, once the code on the Commodore 64 side reads 3 times 50 in hex bytes, then the stack has been filled with F0 bytes long worth of data. So we can see there that the stack is filled with F9, and that's data received from the drive. And then we can see that the code on the Commodore 64 side of things are FE, F9, then primes or loads Y register with F0 in hex. F0 in hex is probably, what, 3 times 50 in hex. Yeah, 5 plus 5 is A in hex, and then A plus another 5 is A, B, C, D, E, F, F. Yes, there we go. So it starts to decode F0 bytes, I think, from the received at the Commodore 64 from the drive. But of course, because it's been using the PHA instruction to store this onto the stack, then it can use the PLA instruction to progressively pull this data. It decks 01, which banks out the ROM, turns on the RAM underneath the ROMs, does another PLA. Oh, look, it does an EOR with F9. Okay, so F9 becomes 0, and then it stores into AE, AF indirected, comma Y. I wonder why the drive code has chosen to EOR, or rather, I wonder why the drive has chosen to EOR the output data to the Commodore 64 by F9. There isn't, I can't really think of any technical detail why you would want to change the values just by XORing them or EORing them with the same value all the time. There doesn't seem to be much benefit from doing that. But it is baked into the tables that are used to decode this data from the drive. Raw bytes, the raw encoded data from the disk, stored in the drive's memory and then sent over and decoded into serial port register updates on the drive code and then read by the Commodore 64. So the Commodore 64 is having to do an extra EOR, whereas the drive code doesn't, because it's all baked into the data table transformation there. But yeah, this is definitely the receive and then store into memory. It's able to do those pulls from stacks, the PLA instructions, relatively quickly, and then the indirected store is also relatively quick as well, of course, because it's offset by the PLA pull from stack instructions, so that's great. It does a few final PLAs. It seems to throw away those results as well, which is intriguing. It does a final EOR with F9 and then an AND with 3F. Okay, maybe there's a status register or status update status value or something like that. I don't think it's the number of blocks left or anything else. I think it's probably a status value. But that's the very fast transmit and receive loop with this Warp25 turbo loader. Basically 4 bytes from the drive gets transferred and transformed into serial port register updates and then received by the Commodore 64, which then receives a real number of 3 bytes for the 4 bytes which are stored on the drive. That's what it looks like anyway. Let's continue on with the execution, and there we go. We've got a drive store watch store point break at 146. So the Commodore 64 is doing a bit wait for the next serial port data. But this routine here, look, it's doing a load X with 1C01, EORing it with a value at a table with 4D1, and then storing it at 146. Just before then, there is a BBC and a CLV instruction pair. The BBC, of course, is waiting for the overflow to be clear. or waiting while the overflow is clear, and it's waiting for it to be set, and then it clears the overflow again afterwards. Yeah, it's reading data at 1C01, which is data in this case from the head, not to the head, because it's not doing a store, it's doing a load. So this is the drive head. So this is the bit data. So basically the overflow is triggered on the CPU, on the drive CPU, when a full 8 bits are read from the drive's head. And it shifts these bits as it reads them from the disk, and then once it's got 8 bits, it signals to the CPU by using the overflow that there needs to be data to be processed. So then the CPU has just about enough time, because you're dealing with mechanical spinning disks, right, underneath the head. You only have a very short amount of time to read the bits from the head before the head needs to start shifting in new bits. Okay, so once the CPU has cleared the overflow, it will have a very, very, very short window in terms of the number of instructions before the next group of bits, 8-bit value, is read from the head. So anyway, the drive code is reading these bits very quickly, EORing them very quickly with a table lookup value, and then storing them with a semi kind of like unrolled loop, although it is using index values. It's doing it 4 chunks at a time. It stores it into those memory locations at 1, 4, 6 onwards, which correspond to those locations which are then used during the serial port register updates. Look, so we have got 146 there, we've got 700 in hex, we've got 751, and then there is a final update as well underneath, which was 7A2, was it? Let's finish writing these notes and then just go back and check. Yeah, 7.5, the final store at 7A2 at 5FA, store A with 7A2, Y as well. So yeah, we have 4 memory ranges, 4 blocks of memory of 50 in hex bytes long, being used to buffer the data from the disk head as the disk is spinning underneath the drive head, which is incredibly compact and time critical code. You can see all of those BVCs and CRVs. I don't think the BVC instructions loop around for too many times before the next group of 8 bits are ready at the drive head input data register or output data register. In this case, it's obviously doing input because it's doing a load accumulator rather than a store. I've just noticed a typo. These are all addresses in the Commodore 64 address space, not the drive's address space. So let's change that to C colon rather than 8 colon. I wasn't looking at code on drive 8. I was looking at code in the C64 at that particular point in time. That makes a lot more sense for the debugging notes. Sorry about that. So I'm just checking to make sure if there's any other drive ROM routines being used during this Warp25 turbo load. So we seem to have, I'm just putting some breakpoints there. No, I mean, I think, so if we continue executing again, let's remove that breakpoint. I don't think we're interested in that. Memory address, are we? No, I think this is just kind of like block reading and block update. There we go. We seem to have a loop of reading blocks. So I think this one reads, the routine at 420 reads the next block, track and sector information. Then the drive is using this optimized table-based serial port data send and also partial decode. So when receiving bytes from the drive, it seems to do one table-based decode and then storing it into memory, and then the serial port send also seems to incorporate some perhaps table-based decode, and then of course using tables to update the serial port registers. But I don't think there's any other drive ROM routines being used at this point during the Warp25 load, because we can see the VIA2 registers for dealing with the head data being accessed directly. So we can check for drive ROM routines being accessed by putting a ranged breakpoint in the drive ROM area from C000 to FFFF and allowing the execution to continue. Let's see what we get. Let's remove some of these other breakpoints because we're not interested in those now. They're in the RAM. There's the drive code. And there we go. Wow. Okay, so it finished the load and then it hit EB4B in the drive ROM. EB4B in the drive's ROM is... which routine is that in the middle of? It's not very descriptive. Let's scroll up a little bit, see what we get. It was... this is doing some memory initialization. Oh, look, it's kind of like in the middle of the reset routine by the looks of that. So the power on reset routine for the drive, it's jumping back into the middle of that, where it's doing some memory initialization. Okie dokie. So we'll delete all the breakpoints. We'll continue on the execution. And there we go. The multiplexer demo has started running. So yeah, wow, there really is no more drive ROM routine being used during the Warp25 load once all of the bootstrapping has been done. So when you're dealing with a disk spinning underneath the drive head, you need to synchronize to the data that you're reading in before you know that it's good data. So usually before every significant block of data that you want to locate, you have a small kind of like sequence of bytes that you would expect to read in, which is kind of like your notion or your concept of track and sector, for example. Now, when you have customized formats, you don't necessarily have to adhere to the standard track and sector formatting and sync marking and stuff like that. So this routine here seems to look for an expected sequence of a very short sequence of bytes read in from the head, and it seems to look for those repeatedly. I think what this is doing at the moment is that it's encoding a few values into sequentially into memory. So it's storing into 1A7 52, it's storing into 1AB, it's storing into 1A8, it's storing into 1A9, and it's storing into 1AA and 1AB. And it's using tables at 3D3, so it seems to be taking some input values and then transforming them with that table at 3D3, and then storing it into some temporary workspace area at 1A8 and 1AB, 1A9. Is there anything else? 1AB, 1AA. Just making sure that I'm trying to capture all of that temporary workspace area. And then it JSRs to 6A0. Oh, and 1A, yeah, so 1A7 as well. 1A7, 1A8, 1A9, 1A, and 1AB. At 679, it JSRs to 6A0, and then it does a BCS check. Carry is often used to indicate success or failure. Then it does another overflow flag, wait, and then, look, it's getting data from the drive head at 1C01 there, at 681 in the code. It's getting data from the drive head and comparing it with that short encoded byte table, if you like, at 1A7 to 1AB. So that's what looks like it's looking for a sequence of bytes, raw data bytes, read from the drive head as the disk is spinning around. It's waiting for this encoded sequence of bytes to indicate that it is at its next concept of track and sector, or track data offset, or whatever it uses internally to denote a chunk of data inside the whole track. So a whole track is much longer than 350 bytes worth of data. It's got a whole bunch of data in there, so you need to identify these F0 times 4/3 amounts of data in the track before you start squirting it out and sending it out to the Commodore 64. So that's what this code here does, is that it looks for a precise data marker before then sending data or interpreting data with those tables, and then eventually sending that data that's been read out to the serial port registers. All of the drive ROM code does this very similarly, but it uses GCR encoding. This is not using 1541 format GCR encoding, it's using a different one. And that's because 1541 standard GCR encoding uses 5 bits to represent 4 bits. This is different. This is not that ratio of bits. Yes, here's that code at 6A0. X seems to be used as a timeout value, perhaps. It's just doing load A with 1C00, and it's doing a BPL to 6C0 to so 6C0, put a breakpoint there. It seems to be waiting for a positive value. So it seems to be so the mark between blocks of data, or the area between blocks of data, seems to be all ones, or FF in hex. But if you get from the drive head, if it seems to be saying that if you get a positive value from the drive head, then that means you have reached the end of your between data synchronization marking, and then that's where, yeah, and it seems to be doing this a maximum of X and Y index times as well. So X and Y seem to be used kind of like a timeout check. So if it's failing to read this interdata or between data synchronization marking, then the disk format is probably returned back as bad or something, and it fails out, or it resyncs or something. But in this case, the BPL at 6C0 is a success. So there we go. This is now success. It reads in the next byte, clears the overflow status, and then says that the carry is clear, so everything is fine. And then basically it waits for the next group of bits to be returned, or flagged rather, as ready at the drive head, and then it proceeds to read the data from the drive head. So yeah, that's the synchronization, the inter between data block gap check, if you like, the sync mark check. So the standard 1541 GCR encoding scheme uses 5 bits to represent 4 bits. So 5 divided by 4 is a size increase of 1.25. So 1 byte becomes 1.25 bytes long, or in other words, 4 bytes becomes 5 bytes worth of data. And here we have a different length. So so instead of 1.25, it's 1.33 recurring. So that means that the Warp25 format is less efficient than the 1541 standard GCR encoding format. So, but there's a trade-off, right? So the Warp25 format, for its data encoding on the disk, is less efficient, but it's quicker to, quicker to decode with those tables and then send to the Commodore 64 over the serial link. So it's pros and cons, right? You have a slightly less space efficient format, but it's faster in code on the drive side of things to decode that data and then send it over the serial port. And then the Commodore 64 is able to decode it nice and quickly as well. So you get these cost benefits to this. As a last step, I think I'll use my updated and tweaked version of C1541 to analyze the G64 file that was created with this Warp25 turbo loader. So we'll just have a little look at the format of that. So the directory listing only has 3 entries. If I use the bpeek command, which reads track and sector information, then we can see that actually these tracks and sectors using hex notation are the track and sector pairs that were loaded with the job code mechanism, which are using 1541 GCR encoded data, and that's because the job code mechanism, of course, because it's using the 1541's ROM routines, it's expecting the data to be in 1541 standard format. But those are those 4 extra blobs of data that are loaded with the job code mechanism way back at the beginning of the bootstrap process for this warp loader. Now, there is a file, of course, which starts at track 18, sector 14, was it? I think it was. And that file contains the initial bootloader, and it's only 1 block long of 171 bytes long, I think it was. But this chain is okay. So yeah, okay. So that chain of data, sorry, it was 1 sector, 1 block, and then 171 bytes long. Of course, each full block is 254 bytes long. But if we have a look at the directory listing for the real file, the test multiplexer demo, then it says that it starts at track 1 sector 0, but when we use the bpeek command, there is no track 1 sector 0, and that's because the 1541 tool expects standard GCR encoding of the data. But if we update it with the we use the updated command GCR peek, track 1 offset 0, then it enables us to dump all of the raw GCR bytes which are being read or written to by the emulated drive head. If we compare the original GCR formatted disk image, then we can use the tool, the C1541 tool. We can use that to read the original track and sector information, and that's because it's 1541 GCR encoded. We can see that, right? So if we use GCR peek track 1 offset 1, then we can bpeek it. Bpeek reads GCR encoded data, and I can read every track and sector on track 1 of the original disk before it was written. But the Warp25 format disk doesn't allow anything on track 1 to be written as GCR encoded data. So there we have it. I think that's a full run through of the Warp25 turbo, saver and also turbo loader. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.